Assalamu alaikum. Welcome to the first tutorial of the fall 2023 semester. Because we gave you a break for the class, so I am uploading this tutorial as a video. Otherwise, we would have done it together in the class. But by giving you this break, you have hopefully a little more time for your presentation. So this tutorial means that there is a problem solving session, and just before the midterm we will now solve all the questions of quiz 1 and quiz 2. So it will serve two purposes. One is that it will give you a good preparation for the midterm, and second, that if you have any doubts, any questions about your solutions of quiz 1 and quiz 2, now they will be cleared. So even after this, if you would like to come to my office to clarify something, you are most welcome to do that, even till the very end of the semester. Let us start with quiz 1, and then we will follow it up with the other quiz. So this is question 1A, which means the multiple choice part of the question on quiz 1. So let us see. Materials that produce electric field when exposed to mechanical force or exhibit mechanical stress when subjected to electricity are called piezoelectric materials, shape memory alloys, nanomaterials, electronic materials. So of course you know that the answer is piezoelectric materials. They are the materials which can undergo mechanical stresses when electricity passes through them. Second question, new processing techniques to improve product life and fatigue properties are which ones? Isothermal forging IF, powder metallurgy PM, die casting DC, and the choice IF and PM, which means isothermal forging or powder metallurgy. So if you had gone through chapter 1, which was just modern materials and so on, then this answer, isothermal forging and powder metallurgy, are the techniques that improve product life and also the fatigue properties. Next question, fullerene and graphene are types of what? Nanomaterial, electronic material, biomaterial, composite. So those of you who have quickly gone through the notes of the book, fullerene and graphene are types of nanomaterial. Next, most abundant metal in the Earth's crust is which one? Abundant means the maximum amount of which material is there. We showed you a graph, a table, and so on about it. Silicon, iron, aluminum, sodium. So the most abundant metal, we are not talking of non-metals like nitrogen and oxygen and so on. So silicon is the most abundant one, and we especially talked about it that the future is all electronics. So we have, I don't know, hundreds of years of material in the Earth's crust for silicon and electronics and so on. Next question, most important material property for high-speed civil transport is what? High-speed civil transport means an aircraft which is a very large one, 300, 400 seats, and we want it to be supersonic, high speed. So temperature resistance, impact strength, hardness, all of the above, right? So you see, all of the above, though we need all of these, but we are saying most important. So we have to give only one property, and we told you that when it is, I mean, a very huge big aircraft and it is going at a supersonic speed, then the maximum problem will be the temperature rise due to friction against air. So temperature resistance will be the most important property. Here let me just remind you that you see in each chapter I have made lots of questions of multiple choice and true false type. So here in a practice tutorial session, I will go through only a few of them. There are of course others and so on, but if you attended the classes regularly with understanding, and if you quickly gave a scan, right, of going through the lecture notes in the book, then most of these things are understanding issues, not memorizing issues. So they will be done, but I cannot go through all of the MCQs and so on. This is now question 1B, which means that it is the true false part, and it is still quiz 1, of course. First question: smart materials change their properties when exposed to specific temperature, stress, light, humidity, etc. So what is your answer? Yes, it is true. Next, shape memory alloys and piezoelectric materials are special types of composites. What is your answer? No, it's false. These are other materials, not composites. They are smart materials and so on. Fiber reinforced plastics are a type of high strength polymer blend. What is your answer? It is false, because no, fiber reinforced materials are composites. Next, plastic alloys are blended polymers. So these are two names, plastic alloys or blended polymers. Are they the same thing? Yes, this is true. Last one on this slide: nickel based high temperature super alloys are modern aerospace materials. What is your answer? Yes, it is true. So these were the multiple choice and the true false parts. We will now start the numerical solution part of the quiz, inshallah. So let us go to question 2A of quiz 1. Draw simple force deformation graphs showing elastic behavior of metals and rubbers polymers. For metals, show plastic deformation and elastic recovery after removal of force. So what I would encourage you to do, if you are doing this tutorial as a good revision exercise and a preparation just before the mid, then pause my solution right now and resolve it on a rough piece of paper. And once you have done these small graphs, then see my answer and then compare. And do that for every question that we are including in the tutorial, right? That whenever the question comes, immediately pause and you think that what is the answer. Once you are sure, then look at the solution. Then it would be a very good practice. So now going back to the question, right? That this is the question. So remember, it is a force deformation graph, not a stress strain graph. So this is the first thing, that please do not write a stress and a strain there on the x and y axes. Write force and deformation. Otherwise, one part of your question is already wrong. So in the first part, we are just asking to draw simple force deformation graphs showing only the elastic behavior of metals and rubbers polymers, only the elastic behavior. So let us see if you have already done it. This was part of the lectures also, and it is part of the slides also, and so on. So it's a very simple thing, right? You have force and you have deformation. If it is a metal, then the elastic portion is a straight line, and you must draw the arrow on the increasing side and decreasing side, which means that when you apply the load, it deforms, and when you decrease the load or remove the load, it goes back to zero deformation. For polymers and rubbers, which are non-linear elastic, non-linear, right? So it is not a straight line, it is any curve. But again, this arrow means when you increase the force, the deformation is increasing. When you decrease the force, this arrow means it is decreasing. But after you have removed all the force, it goes back to zero, right? So it is a non-linear curve, but because when you remove the force, the deformation goes back to zero, so therefore it is still elastic. So again, right, it is a very simple thing. We spent 5 minutes or more on it during the lectures. It is in the slides, it is in the book. So most of you, alhamdulillah, got it right, but some of you who did not, then they should think about it, that you see, this is a very basic fundamental of both material science and solid mechanics. And right, Okay, so now the second part. The second part for metals, show plastic deformation and elastic recovery after removal of the force. Right? So now we are not asking of polymers, only metals. But this was only elastic. Now we are saying go to plastic deformation and show elastic recovery. So again, this is the diagram which we showed in the class, discussed it. It is in the book also. So once again, we have force and deformation. But now this was the linear portion. Then there is the non-linear portion. And in the plastic non-linear portion, anywhere, when you remove the force, then you remember that this line will be parallel to the initial line. So here you are increasing the load, here you are decreasing the load. But now when you remove all the force, it is still at this point. So there is some permanent plastic deformation. And from here till here, this area is the elastic recovery. That at the time you were applying the load, this much of deformation was there. But when you remove the load, this much of deformation went away. So any deformation that goes away is the elastic part. So you are showing the full elastic plastic behavior of metals. And then you are showing that if you have gone to the plastic region, then when you remove the load, the line will be parallel to the initial straight line. And at the end, some of the deformation will be removed, which is the linear recovery, elastic recovery. And the remaining permanent will also be there. So this was the 2A part of your quiz 1. Let us now start with question 2B of quiz 1. Aluminum alloy 6061 T6 has yield strength of 270 megapascal, elastic modulus of 70 gigapascal, fracture stress of 310 megapascal, and ductility of 17%. Find the modulus of resilience UR and the modulus of toughness UT for this alloy. What is or are your major assumptions? Draw a rough stress strain sketch. So once again, I would request that please stop the presentation, pause it, solve it, and then come back. I'm showing you here two general behaviors of all metals that either after the elastic limit, there is this small fluctuation and then it goes up, or it continuously goes up. So there is a linear portion and there is a non-linear plastic portion until fracture. And you know, elastic behavior, plastic behavior, strain hardening, necking. So ultimate strength, fracture, all those points are there. So this is a general metal. This is a general metal. So I will normally assume that we are talking of this type of a metal, right? This type of a metal. But when you want to find the modulus of toughness and resilience, then, right, your answer is, for example, that the modulus of toughness is the area under the whole curve. And the modulus of resilience is only the area under the linear portion of the curve, right? So modulus of resilience, if this is the end point, then draw a line here and all this area will be your modulus of resilience. And draw a straight line from here and all the area will be the modulus of toughness. But then how will you find it? This is a curve. This is a curve. So how will you find area under the curve? Therefore, you will have to make a little assumption. And that is what we are asking. That what will be your major assumptions in doing this, right? And how will you solve it?